Even though there have been very many years in western Colorado, with ample water to turn the pastures a bountiful and lush green, this past year of 2021 was not one of them. Blue Mesa Reservoir on the Gunnison River revealed an expanding bathtub ring and was just a single indication of the extended trend of drought occurring throughout the western United States. At the time of this video, water stored in Blue Mesa was near record level lows, holding only 27% of its full capacity. This left the utility-grade hydropower collection tower at its lowest level since 1984. The excess springtime water releases of 2015 at the nearby Morrow Point Dam may become a thing of the past as climate change continues to overtake the North American Southwest. But this channel is about microhydro. Even where you find fields being irrigated from meandering water ditches, you will find the potential for microhydro. This video is about a system utilizing irrigation ditch water, which first travels from the ditch through an underground pipe. It then enters a distribution box and again goes underground to another box where a Coanda screen removes any large debris. From here it drops to the fields where it can be used for irrigation or microhydro. The irrigation water rights are long established on this property, and with the existing natural head pressure, it is an appropriate place to harness power with a microhydro system. Several companies and agencies came together to design, fund, and install the system. There are links to some of them in the comments section below. First, let's discuss a little bit about how this project was constructed. With the 12-inch penstock pipeline buried and in place at a sufficient depth, the precast concrete vault for the system was installed. Once this was completed, a pad of crushed rocks was formed and leveled to hold concrete deck blocks. The frame which would make up the base of the powerhouse is bolted to the concrete vault and supported on these blocks. With the 12-inch penstock now in place and the vault properly situated, a 12-inch corrugated tail race for the system will carry the water away to an exit ditch. A simple outbuilding was constructed to house the necessary components for the system. This was wrapped in Tyvek, steel roofing, and siding. The 12-inch penstock was reduced to an 8-inch pipe via a reduction fitting at the lowest point with a Z-pipe that will bring the water into the building. Both a fitting for an air relief valve and an 8-inch butterfly valve are installed to be above ground. A drain valve is installed at the lowest point of the penstock to permit draining the pipeline. This is to facilitate any repairs and prevent freezing damage should the system be shut down in winter. With the penstock components assembled, let's start to take a look at how the system runs. The heart of the power generation is achieved with two turbo impulse turbines, each capable of harnessing 4 kilowatts. The turbines are mounted vertically on sleeves above the concrete vault, and each has 4 changeable nozzles to supply water to drive the turbo runners. A horizontal manifold pipe distributes the pressurized water to the 8 nozzle feed tubes. There are 2 fully manual valves and 6 pressure-controlled actuators which manage the available flow to the turbine nozzles. So each turbine has a potential to harness power from 1 manual valve and 3 automatic valves. The penstock manifold is also fitted with a large expansion tank to soften any pressure variations when the automatic valves actuate. With 64 pounds per square inch in the penstock, the head of the system is roughly 147 feet. Each of the actuators is controlled by a shutoff valve to enable any required service. And each of the actuators is controlled by a pressure sensor which can adjust flow depending on available water. Let's have Gabe Stevens, the general contractor on the system, give us an explanation of the system.
Okay, so general rundown on this system, we basically have two 4-kilowatt systems running in parallel to one another. Right now, there's only one side of it running, 4 kilowatts, due to low water this time of year, and especially this summer, being in a drought. This system runs off of irrigation water. So how this works, wild AC power comes off of the generator, runs into the disconnect, runs into the controller and rectifier, which converts the AC signal to a DC signal, and that's what feeds the inverter on a DC input. It's a standard solar inverter, and everything is the same as a grid tie solar system from here on out to the grid. The controller not only converts the signal from the wild AC to the DC signal for the inverter, but it also acts as a shunt diversion. So if the grid goes down, it will take the power from the hydro generator and will shunt it in this resistive load as heat, and that's just a safety precaution in case the grid goes down or there's some other issue. And that's the gist of how the system works. All the switches are set at different pressures, and this way it modulates how much water is coming through the entire system based on how much pressure is in the line. So if, say at this property, more water is being used in some of the center pivot irrigation, that means that there will be less water in the penstock above this system. That will lower the head pressure in the line, and these switches will open and close these valves based on what's happening there. So that way we ensure that no water is wasted coming through the property. All the available water comes through this system. It's either redlined at 8 kilowatts with all 8 valves open, or we can run down to 1 or 2 valves that low. So on this style turbine, with the nozzles like this, this turbine comes from High Power Hydro, that's HI power. They are high head impulse turbines, and you can typically find these anywhere ranging from I think a few hundred kilowatts from companies such as ES&D out to about 4 kilowatts from these guys, High Power Hydro. High Power does 2 and 4 kilowatt versions of these turbines. We like to use fire hose couplings. They just make it really easy out in the field. If you need to get inside of here to, say, take off a body here for a nozzle, to change out a nozzle with a different orifice, you have to do that sometimes with seasonal variation in your flow. And this is just a really hot ticket right here. Get a hold of some of these. Your farm supply stores will typically have them in stock. And you want to use this T-bolt clamp fitting. This does much better than a standard hose clamp for these high pressures. You can really crank on these things, and they're really strong. I've yet to have one of these fail, and it's well worth your time and money to go this route. You will save so much more headache in the long run by doing that. So this controller also comes from High Power Hydro. It's a good idea in our experience to find spare capacitors to keep on site for these, because every now and then they will go out. Having a fan is a good idea as well. These fans were added on after the fact. Just helps to keep things cooler in here. Okay, so say if your system's been sitting, depending on the configuration of your system, the ones that we have to do here in Colorado, we have a turbine side disconnect, which is for the wild AC signal coming to the controller. Just want to make sure that's on. DC signal leaves the controller, comes into the inverter. We have a disconnect here as well. Want to make sure that's on. And then inside the panel here, we have a breaker for the inverter as well, which is AC power to the inverter, which we have on. Generally want to know on, say, a 4 nozzle or a 2 nozzle turbine like this, you want to kind of know what nozzle you want to start with. Sometimes it's a smaller or a larger nozzle. In this case, since we have the automated valves, each turbine has 3 automated valves with 1 manual valve. We call this the idler valve, and basically it means that if we lose all power in the building, because these run off AC power, if they quit working, we can always control manually with this guy, or if everything shuts, the turbine will stay spinning and will have the ability to engage back with the grid. So basically it's just a way to have a manual option in the system outside of everything else that's automated and reliant on grid power. So these style turbines, you always want to ease into them. That's the case with most of the turbines that I've dealt with, also that are not impulse turbines like this. So we just want to start real slow. And you want to listen. You'll hear the turbine gain speed, but you want to go really easy. So I'm going to open it just a little bit. I'm only about 25% open. So my controller has a green light on it now. That means that the controller has accepted the signal from the turbine, so far we're good. It has a yellow flashing light on the controller, which means that it's being diverted to the dump load right now. If you look at the inverter, it has a green flashing light, meaning that it's seeing the DC signal. It's working through things right now, making sure it likes the signal. It usually takes a couple or a few minutes for it to decide it likes it before it will connect with the grid and start backfeeding to the grid. Until that happens, it will be running through the dump load from the controller. We'll know when this light turns solid green and quits flashing that we're now connected to the grid. It'll take a few minutes probably. There we go. We're locked in. Okay, so now that we're locked in, we're going to start opening things up.
With this episode, I wish to begin presenting other microhydro systems with very different design approaches from my own system. And if you haven't seen my other microhydro videos, I invite you to take a look and subscribe for any future videos. There's a link in the comments section below.